Solving general chemistry problems in electrochemistry. So electrochemistry is clearly important for energy storage and generation. An equally important field of application, however, is that of chemical sensors. These are devices that are able to measure electricity very accurately. Our electrochemical theories allow us to relate electrical measurements on a cell to chemical properties. Some of the most sensitive devices for determining the type of species present and/or the amount of some material that is present are electrochemically based. A very wide range of techniques have been developed over the years. We'll look just at a few of the more general and widely used devices and procedures. The measurement of voltage or current are the most obvious properties of an electrochemical cell. These lead to broad fields known as potentiometry and amperometry. Voltammetry involves the controlled variation of potential while measuring the resulting current that flows. Another important technique measures charge and is referred to as coulometry. For now, we are only able to just touch on a few examples of these techniques. The actual range of application is enormous. The most common way of measuring the concentration of hydrogen ions in a solution is with a pH meter. You can think of P as being a mathematical operator that takes the negative of the base 10 logarithm of something. That something in this case is the H, and the portion of pH, and that's referring to the hydronium ion concentration. Hence, pH is the negative base 10 logarithm of the hydrogen ion concentration of a solution. A probe to measure a solution's pH is arguably the oldest electrochemical sensor we have. As such, many variants have developed over the years. In the picture above, you see the probe inserted into the solution in the beaker. The rest of the device is just to hold it securely and provide the electronics to calculate the pH, display it, and provide any additional computational functions. But as for the electrochemical probe itself, well, here is one implementation. In this case, we base the probe on the silver-silver chloride electrochemical couple. There are two different solutions inside the probe. The first is a KCl, potassium chloride solution that is saturated. It's held in place by a porous membrane. We use a saturated solution because you can leave some KCl crystals inside, and if the chloride concentration decreases for some reason, more KCl will dissolve to keep the same concentration. If the concentration increases for some reason, some KCl will precipitate out to again keep the same concentration. A silver wire with a coating of silver chloride is submerged in its solution and becomes the chloride concentration. And because the chloride concentration is constant, the potential on the wire is constant and becomes the stable reference potential for our measurement. Another chamber inside harbors another silver-silver chloride electrode in a solution with a controlled pH, say a buffer solution at pH equal to 7. This chamber extends to the outside of the probe and ends in what is usually a spherical glass ball. It's made of a special glass material that allows the diffusion of hydrogen ions. The glass is very thin and needs to be treated carefully. The probes are designed to help you use it properly, but you can break them if you try. The H+ ion concentration inside the inner chamber establishes a concentration of H+ ions along the inside of the bulb. A different concentration is formed along the outside of the solution we are studying. This concentration difference sets up a potential difference that is sensed by the inner silver-silver chloride probe, and the difference in potential is measured and amplified by the electronics which convert that voltage through the Nernst equation into a pH. The test solution concentration can vary from 1 molar HCl, for instance, all the way to 1 molar sodium hydroxide on the other hand, and the potential difference can vary by as much as plus or minus 1400 millivolts. The key theoretical aspect in the Nernst equation is that the cell potential varies logarithmically with the H+ concentration. In practice, we calibrate the meter daily, or even more often if your results are critical, with at least two standardized solutions. The probe is inserted in a buffer solution at pH equal to 4.000, and the meter's output is adjusted so that it reads 4.000. It's then inserted into a different solution at pH 10, for instance, and a different adjustment sets it to that reading. This fixes a couple of offset and gain electronic constants in the electronics, which ensures the linearity between the solution pH and the amplified electronic signal. Now insertion into the test solution provides an accurate result. Readings from pH of 0 through pH of 14 are possible, some 14 orders of magnitude difference in H+ concentration. Now this is the first example of an ion selective electrode. the selectivity for the hydronium ion arises entirely because of the chemical nature of the thin glass membrane. By changing the chemical nature of that interface, we can introduce selectivity for different ions. For instance, if we use a single crystal of lanthanum trifluoride, it has a small amount of europium added as a dopant, and then we can selectively detect the concentration of fluoride ions. You could measure fluoride concentration in drinking water, in mouthwash, or in your toothpaste. An electrode selective for calcium 2+ is formed by a thin polyvinyl chloride film being impregnated with a large organic molecule. It's a phosphate diester such as C10H21O taken twice for PO2-. And it selectively binds to calcium 2+ and allows it to migrate across the film. Calcium in water or other fluids such as milk or even blood samples can now be readily measured. A lead selective electrode can be formed using a thin crystal of lead sulfide doped with silver sulfide, which increases lead ion mobility. This provides an excellent tool for measuring lead concentration in water or other samples. From these electronic signals, we could report the ion concentration and molarity, or as, respectively, PF, PCA, or ppb. The P function can be applied for any substance, not just pH. Carbon monoxide detectors are becoming essential safety devices in homes and workplaces. Carbon monoxide is a gas that competes with oxygen for binding to hemoglobin in our blood. It gets on, but won't get off. With sufficient exposure, our blood is not able to transport oxygen throughout the body, and asphyxiation and death are the result. There are several different kinds of detectors. Some take longer than others to detect a dangerous condition and sound the alarm. Some provide accurate readings of concentration, while others just sound an alarm when a threshold has been crossed. The best type is an electrochemical version. It provides the fastest response and a readout that is linear with CO concentration. The basic design consists of a container with sulfuric acid as an electrolyte, and which has 2 electrodes. It is covered with a polymer film that allows the transport of gas, but keeps the electrolyte from spilling out. At the anode, carbon monoxide can be oxidized to carbon dioxide, while at the cathode oxygen is reduced. Now this is like a fuel cell, and the resulting current can be detected and is proportional to the carbon monoxide concentration. The basic reactions are given here. Now this is an amperometric device, as it is measuring current rather than potential to determine the CO concentration signal with which it must determine whether or not to sound the alarm. Another application of electrochemistry is the glucose monitor. Diabetes mellitus, or just diabetes, is a metabolic disorder that's increasing in the world. Almost 9% of the adult population worldwide suffers from this to varying degrees. A key to successful treatment and management is the accuracy and ease of testing an individual's glucose level in their blood. Glucometers have been developed to help with this. A patient pricks their finger with a sharp lancet. A detector strip provides a capillary pathway into the detector for the blood when touched to the drop of blood on the patient's finger. The capillary ensures a specific volume of blood has been sampled. The blood is exposed to a surface on which has been immobilized an enzyme that will catalyze the oxidation of any glucose present. Using the enzymatic pathway helps to ensure that the test is specific for glucose and not the host of other oxidizable molecules found in a sample of blood. 2 enzymes are commonly used, glucose oxidase or glucose dehydrogenase. One is more sensitive and the other is more specific. Different catalysts are used in different situations, leading to different detectors with different results. The oxidation of glucose to gluconolactone is coupled with the reduction of oxygen to produce hydrogen peroxide. The overall reaction is given here as well. Now, the very first glucose sensor used an oxygen electrode that detected the amount of oxygen consumed in these reactions. Since then, it has proven to be more reliable and reproducible to transfer that molecular signal to other molecular systems that can be probed electrochemically with more accuracy. One common approach now is to include an amount of ferricyanide ion, FeCN6 3-, which readily reacts with the hydrogen peroxide from the initial reaction in order for it to be reduced to the ferrocyanide ion. It is this ferrocyanide ion that is electrochemically reduced back to the ferricyanide ion that is the measure of the concentration of glucose in the original blood sample. Some units will measure the current that is generated during this reduction and relate that to the glucose concentration. Other units will collect the total charge charge is equal to the integral of current over time, pass to complete the conversion back to ferricyanide, providing an accurate readout. As such, it would be a coulometric device. Throughout modern industry, multiple layers of thin metallic films are commonly applied to structural substrates to improve a device's performance. We may be wanting to make a plastic part with an electrically conductive outer layer. We may want to prevent a steel component from rusting. We may want to make a feature to have a bright, shiny finish. We may need a substance to have a particularly hard outer layer to improve its durability. Automotive parts, bathroom fixtures, electronic circuit boards, all of these and many more are modified by the application of thin films in order to provide the performance required to fulfill the task at hand. These films are applied in a multitude of ways depending upon the desired outcome. Physical vapor deposition, chemical vapor deposition, electrochemical deposition, electrolysis deposition, and so forth. And it is usually the case that a single metallic layer is insufficient. Usually multiple layers must be deposited on top of each other. Each layer has a role to play in the overall device performance. That layer must achieve a certain thickness in order to ensure it does its job. But if it is much thicker than is required, then that is an additional cost that is unnecessary. When manufacturing such a part, it is essential to continually check and confirm that the process is producing components with the film thicknesses that are within the required tolerance ranges. The automotive industry might well be one of the most demanding in this area. As an example, here is a complex film that can be found on some substrate material, which could be structural metal such as steel or aluminum alloy, but could also be a plastic such as ABS or PVC. In this case, we find 8 different metallic layers ranging in thickness from a few tens of nanometers to several tens of microns. For comparison, a human hair has a thickness of around 80 to 100 microns, so each of these layers is considerably thinner than a hair's width. And yet the overall final performance of the device critically depends on each of these layers performing their task perfectly. It starts with an adhesion layer of perhaps 50 nanometers thickness, whose purpose is to ensure that the film adheres to the substrate. On top of that, a couple of copper films of different compositions are formed, followed by several nickel layers. Each layer's role ranges from one ensuring structural integrity to another providing a pleasant shiny finish, or one ensuring chemical inertness or perhaps matching thermal expansion characteristics. There's a whole host of properties that need to be considered and optimized. A Akulascope is a commercial device that can be used to measure the thickness of each of these films while confirming the chemical nature of each one electrochemically. Think back to the Daniell cell. When operating, the zinc electrode was dissolving as it was oxidized as the anode. For a battery, we wanted that electrode to last as long as possible in order to have a long-lasting battery that would deliver the needed electric current. The Killerscope takes the same idea and dissolves these metal films in a small, controlled test area, monitoring the potential, which helps to identify the chemical nature of the film currently dissolving, and the current, which is related to the rate at which the film is dissolving as a function of time. Each time one layer is dissolved and a new one starts to erode, there is a change in the potential measured. The integral of the current against time is the total charge that was passed, and that can be related to the amount of material dissolved when we know the stoichiometric relationship between electrons and the metal atoms involved. This is coulometry. When the area of erosion is tightly controlled and the density of the material is known, this measured amount of material can be used to precisely calculate the thickness of each layer in this complex film. The Killerscope uses a small probe. That's an electrode with a plastic ring that defines the region of electrochemical activity. This controls the area being eroded. An electrolyte fills the cavity inside and on top of the film to be studied. A silver chloride electrode is used in the solution to measure the potential, and an applied voltage helps to drive the reaction in the desired direction. As an example, consider this copper-nickel chromium film. A typical film may consist of these 3 different metal layers, each with a specific thickness. The Killerscope can be used to confirm both the chemical identity and the thickness of each film. The Killerscope probe is brought up to the surface and pressed firmly against it to ensure a liquid-tight seal. The electrolyte is introduced, and electrical connections to the substrate are put in place. A sufficient potential is applied to obtain the desired current flow, which controls the rate of reaction. The metal sample is the anode and is being oxidized. The silver chloride electrode probes the potential between it and the metal that is currently being exposed. The first observable is then the potential. Notice how the potential moves quickly to a new value when the chemical nature of a layer changes. The operator uses this information to confirm the chemical nature of each part of the film. At the same time, we monitor the current that flows. This is both a function of the material and the voltage we may be applying. But whether we remove it quickly, a larger current, or slowly, smaller current, the total charge passed, which is the integral of the current versus time, recall that's the area under the current time curve, it's uniquely related to the amount of material dissolved. A third graph can be formed that is the value of this integral versus time. With this information, the identity and thickness of each layer in an even complex series of films can be readily confirmed, ensuring the continued operation of the manufacturing line.